how can I prevent my suboptimal coders from fucking it up and having integer overflows all over the code? I just specify that my length field is a maximum of 30 bits. That means they actually have to add 4 values to get their integer overflow. That is smart. This is how you write good specs. But then again, they also use variable length integers. Let me tell you something about Flash and the whole stuff. So they love to build very complicated data structures to save about 2 bits. And then the next entry in the data structure says 2 bytes reserved, must be 0. This being a tradition, they carried it on in the AVM too. Now, so there's only so many ways you can have a variable length integer. And they're between 4 or 8, depends on how you call. So Adobe, with their sureness, picked the worst possible way to do it. So I actually had to check out the Tamarind source code to figure out how it works, because the specification wasn't clear on this. And this is what I found. Now, if you speak a little bit of C, let's ignore the style of this code and ignore the fact that you could actually do that in a loop. However, just watch the last 3 lines. So you're taking the last byte and shifting it 28 to the left and adding it to the result and then returning the result. How many bits did you actually parse? Is it 30? No, certainly not. So the lowest level reading function that is supposed to read your save 30-bit length fields of the SWIFT file, or no, of the ABC part of it, already ignores that specification and returns 32-bit. Congratulations. I hope the spec guy never saw that. He's probably dying or resigning. So what are the considerations for the defense approach here were, there are 2 types of attacks that we need to handle. One is malformed files that fuck up your Flash player. The other one, who's calling me? Whoever it was, he hung up. So anyway, the second part being Flash files that are well-formed, but they use the API to do some stuff that you don't actually want to see. The idea was like, well, you could go ahead and try to fix the player. Kind of. You don't want to instrument it. The player is closed source. It changes all the time. So you will have to have a horde of reverse engineer monkeys or students or whatever your resource is to constantly check where all the offsets went and where all the functions are. The player is extremely forgiving in parsing bullshit and executing it. So it's certainly not what we want. The player also only parses things that it actually needs right now. So for the website operator scenario, it's useless. And the player is written in unmanaged language, so every time they fuck something up, it goes boom. And seriously, nobody wants to write a new Flash player. So the idea was, let's try something else. Let's try something that I call normalization through recreation. Fancy name, extremely trivial way. So if the final consumer, which is the Flash player, is inherently fragile, as in it chokes on every wrong input that you can possibly give it, you need to actually filter it before. So what we do is we try to safely parse an SWF file, being really, really strict on the specification compliance and on the formats, then delete the original file and be left with what we understood of this file. And we create a new one. While we're at it, we can also just go ahead and patch the code that we're looking at and make it do other things. And then we take the normalized SWF file and pass it on to the original player in the hope that we clean it up sufficiently so it doesn't die. Introduction. So that tool was named Blitzableiter. Yes, it is a German term. Get used to it. The name was chosen because it takes dangerous electricity and turns it into a little blinky flash that doesn't do anything. So how do we safely parse? We take a runtime that will allow us to safely parse everything. It's as simple as that. So there is this discussion whether you should actually use managed languages or not. The performance issue doesn't exist. It's a myth. Then there is the only other issue that people say, like, real men code in C. Well, real men also fight battles with swords. Why don't I see the United States flying out people with swords? You mean, real men might do this, but like, it's the pussies who bring in the nukes. And like, in a defense scenario, I want to be the guy on the nuke. Also, it's the same lesson that we learned the hard way in crypto. Like, every time someone walks up to you and says, I have this brilliant new crypto protocol and I invented it all myself, you go laughing at him. But if he actually says, like, I followed everything Schneier ever published and I used all those proven algorithms, it can possibly be a good crypto protocol. So that's the same reason to build on a runtime that actually allows us good parsing, which is the CLR. It allows us to prevent any buffer overflow issues that we potentially would have. And in contrast to Java, we also get protection for integer overflows, which is really important in this scenario. We just ensure that we're not running any unsafe code, which the runtime allows. And since we're targeting .NET 2, it actually runs nicely on Mono as well. And the Mono guys don't implement the whole stuff so you can ignore it, right? They actually have a point of bringing this into open source operating systems. There is also a neat strategic benefit of running stuff on .NET. If someone finds a 0-day against the CLR, your little fucking Flash parser is not the one he's wasting it on. He's going to take the biggest SharePoint site that he can find. He's not going to care about your Flash player. So, enforcing the container boundaries, which Adobe never does, is really easy in this scenario because we just allocate new memory every time we find a container, and then if things go out of the container, it throws an exception. We also really have to make sure that we also cover the case where the container actually didn't contain enough data to be full. So there would be stuff left, because that would be where I would put the shell code. So we have to make sure that the whole container was used. We only parse documented data. If you try to parse shit you don't actually understand, it's bound to fail. And the downside of this approach, of course, means you have to parse everything completely. Like, you can't get away with just parsing the things you're interested in. You have to parse the whole thing. And then check the input data very thoroughly on specification compliance. So is the format correct? Is it compliant with the version we're looking at? Are all the reserved bits set? Do the conditions make sense? Stuff like that. And then, of course, you want to do the code verification that nobody else does. So do the instructions actually have a legal length? Is it a legal instruction in this version? Does it actually make sense? How about jumping? Like, does it actually jump to another instruction beginning, or it jumps it in the middle of an instruction, which it is not supposed to do? Same holds true for try-catch blocks and for functions and all that. This is relatively trivial stuff. Like, you can take a linear disassembly and then see whether the jump points actually, the jump targets actually terminate on an instruction or not. And due to this brilliant idea of inline specification of functions, you can, of course, go ahead and specify two functions with bytecodes that would be overlapping. Therefore, we have to introduce a check that actually makes sure that every instruction is only part of one function, because otherwise shit goes wrong. Now, that leaves us with something that we consider a relatively clean format in terms of code and file format. However, it doesn't do anything about the people just redirecting your browser to the next exe download. Static analysis, provably thanks to this brilliant gay mathematician back in World War II, doesn't allow us to figure out what code does. Oh, if you find that out, I would be interested to know. It's called the halting problem, if you want to look it up. The alternative that we could have is we could emulate the entire thing. Like, we could emulate the AVM, see what the code would be doing, and then patch things that we're feeling bad about. The problem is we will automatically run into discrepancies where the emulation actually takes different conclusions than the virtual machine. Because mind you, we're dealing with a closed source, underspecified virtual machine that is very well known for